All right, good morning, Honors Math 4 students. We're going to take a few minutes here to wrap up section 11.1. Where we're talking about tangents, uh, derivatives, and instantaneous velocity, which really are all the same thing. The last problem that we finished up, just to kind of go over the formula for the derivative again, was finding the derivative at a point. So at a point means that we are letting x equal some value a. So our derivative of the function at 4 is telling us to let the point before a be 4. So the derivative of this function at 4 means that we need to use 4 plus h and 4 as our two input values in our function. Once we put 4 plus h into the function, here's our function right here. And once we put 4 into the function, okay, we got that in the blue, we got that in the green, and we simplify, what happens is we have our constants cancel out, and we're only left with terms that have h's in them, which means we can pull out the h's as GCF in the numerator, and then we are left with just 2h plus 16, which is finally the spot in this limit where we can actually let h be 0 because it is now a continuous function. If we let h be 0, we get 16. So the derivative of this function at 4 is 16, or the slope of the tangent line at x equals 4 is 16. You know, we had talked about earlier, I believe in the other video, about how the y value at this point is 29. So at the point 4 comma 29, the slope of the tangent line is 16. I'm going to go through the next example pretty quick here. It's the same process. We have a new function, 4t minus 3. We're going to find the derivative at 3, or the slope of the tangent line at x equals 3. Or in this case, it's t, excuse me. And we go through the same process. We have 3 plus h as an input, and then we have 3 as an input, and then h is our denominator. We're letting h approach 0. That's why we're using our limits here. It's going to help us get rid of this division by 0. As we go through our process and simplify, we end up getting 4 as our value. You get the limit of as h approaches 0 of 4. Well, this just equals 4 then. So the derivative at 3 is 4. And the reason why I'm going through this pretty quick is if you look at what the function was that we were dealing with to begin with, it was a line. So this linear function is guaranteed to have a slope of 4 at any point. So it doesn't matter if this is 3 or 6 or 2 or whatever it is, the derivative is going to be 4. And that's kind of some of the stuff that I've written here on the paper. Actually in the blue down here, it's a slope of 4 in this function. So if we went back to this guy here real quick before I move on, if I asked you to find the derivative of this function at a different point, let's say 5 or 6 or whatever, you'd have to go through this whole process over again. Okay, well, until you learn some of the tricks of the trade in calculus. You have to go through this whole process over again, which is really tedious. So what would be more useful is if we actually had a derivative function. So not just a value, but a function that will tell us the derivative at any point of the original function. So that's what we're going to look at next, is the derivative of a function. Okay, this is our formula for the derivative of a function. It's the same as the one that we had before for finding a value at a. We've just said, well, let's not let this be a anymore. Let's let this just be x, and we'll leave it as x so that we have our independent variable in the function yet. So we're also going to have a new notation here. If you look at our next two examples, find the derivative of this function. So notice there's no value for a now. Find the value of this derivative of the function x squared, y equals x squared. This is the same, is asking the same thing. Find the derivative with respect to y, find the derivative of y with respect to x of this function. So it's kind of like, if we go back to the instantaneous velocity problems that we did at the beginning of this section, we were finding the derivative of the position with respect to time. So we had the position up here, the change in position, and the time down here. You know, we were using the delta y over delta x for slope, which is what we're finding, slope of the tangent line. think of these d's as kind of being the same thing as these deltas here. Okay, that change in y over the change in x. It's just read a little bit differently. The derivative of y with respect to x. We're going to treat it just like we have been treating this guy. So to find the derivative of this function, y equals x squared. Okay, we're going to first, I have the same formula, I just rewrote it, just to kind of make it clear what colors I'm using here, because this is going to be where we put x plus h into this function. So you put x plus h in here and you get x plus h squared. With the green one, we're going to just be using our original function, just f of x. Well, that's just x squared. Then we're going to FOIL, distribute x plus h out, simplify. We're left with all terms that have h's in them, so we're able to find a common factor that we can cancel out. And here's our resulting expression that we can now put h into, 0 into for h. So if we put 0, if we put 0 into here for h, we just get 2x. So the limit of this function, y equals x squared, let me start over again. The limit of this function as h approaches 0 gives us the derivative of the original function, x squared, which is 2x. So the derivative of that function